Hello, my name is John Antonakis. I'm Professor of Organizational Behavior at the University of Lausanne. Today I'm going to talk about a topic that many researchers don't know about or care to avoid: endogeneity. It sounds bad. It is bad. It's like a deadly virus that threatens the viability of models that make causal claims regarding the relationship between an independent variable and a dependent variable. Who needs to know about endogeneity? Researchers, students, but most important, policymakers and practitioners. Endogeneity is always lurking around in the background. Therefore, it is important to know what it is, why it is deadly for research, and how to deal with it. We are bombarded all the time with apparent causal claims that have implications for practice. For example, choosing a certain strategy or control system in a company that apparently predicts the company's performance. Good leader-member relations, or LMX, which apparently predicts reduced turnover intentions on the part of subordinates or increased satisfaction. Having more women on management boards apparently predicts profitability of companies. Management researchers and consultants often make such claims, but are these findings actually valid? How can we know if that is the case? As you will see at the end of this podcast, very often such claims, if they haven't been observed in certain conditions, will usually be false. To better understand the problem of endogeneity, imagine a philosopher who is taken out on a field and is supposed to observe a phenomenon that is going to occur 50 times. Her goal is to piece together what she sees and provide a theoretical explanation of what she has observed. So the philosopher walks out on the field and she stares out all around her. She hears a few birds, the wind rustling, nothing much. Suddenly, a disk streaks across the sky. She hears a loud crack, and the disk shatters into smithereens. Puzzled at this occurrence, she looks again. Suddenly, she hears a streak in the sky. The disk appears. She hears the round crack, and the disk shatters again. This happens several times. Most of the times that she hears the loud crack, the disk shatters. After thinking about this phenomenon for quite some time, the philosopher comes up with a conclusion, a theoretical explanation which stems from the loud crack. She comes to this conclusion after having observed 50 trials, and she's really convinced that it must be the sound that is destroying the disk. Let's take a look at the data that she gathered. So here is the data that shows exactly what the philosopher saw and what she recorded. Over here, there was no loud crack. As you can see, out of 19 trials, the disk remained intact and it was never destroyed. Over here is when she heard the loud crack. On 29 trials where the loud crack occurred, the disk was shattered, and on 2 trials where the loud crack occurred, the disk did not shatter. As you can see, there's a very strong relationship between two variables, that is, hearing the sound and shattering. When the sound is present, the disk usually shatters. In fact, the probability is extremely high. And when the sound is not there, it's almost with 100% certainty that the disk does not shatter. We can actually estimate the relationship between these two variables. This is actually called a phi coefficient, and it is 0.92. It is almost perfect. Therefore, what can we conclude? When the sound is present, it's highly likely that the disk shatters. When the sound is not present, it is highly likely that it doesn't. Now, here's a question to you. Can the philosopher actually conclude that the sound is making the disk shatter? The observed, and I highlight the observed, correlation is very strong and it's statistically significant. That is, this relationship is very reliable and it is not due to chance. but does it actually reflect the true relationship between the sound and the disk shattering? It seems like the crack causes the disk to shatter. Let's talk about the variables in terms of x, the cause, and y, the apparent outcome. Assume the following causal diagram where x in fact causes y, and there's something that causes y too that we don't observe. We call this a disturbance term, the E term over here, or perhaps unmeasured causes. As you can see, the reason why this exists is because we don't perfectly predict when the disk will shatter as a function of the sound. We have a little bit of error, and that was shown in the bar graph. Those are the misses that we have. The problem with this causal specification is that x here is actually not exogenous. It depends on something. And if this something is not accounted for in the model, the relationship that we will estimate between x and y will be in fact very biased. Now here comes the big problem, endogeneity. What causes x might also cause y. That is, u and e, these unknown causes, may be correlated or may be due to the same variable, and this variable is what we call an omitted cause. When adding z in the model, we account for what causes both x and y. In fact, the relationship between x and y is non-existent. It is naught, zero. To better understand why the relation between x and y is actually zero, I estimated a multivariate regression where, firstly, z predicts x, how loud the sound was, using a linear model. Z predicts y, whether the disk shattered, using a linear probability model, estimated with OLS. And the disturbances of x and y, u and e, are correlated. The residual correlation between x and y is actually zero when we account for what causes x and y. For detailed notes and to download the data, please refer to the following link on my webpage. So this is the true model. Z causes both x and y. X is how loud the crack was that the philosopher heard, which is caused by a gunshot, the omitted variable z. What she hears is also caused by u, an unmeasured cause, perhaps background noise, which perturbed a little bit what she heard. The disk shattering is caused by z as well. And e, a random unmeasured cause, could have been the wind when the shooter was shooting, and which disturbed the direction of the bullets, which is why they missed. So this was a random cause which is unmeasured in the model and uncorrelated with z. Going back to the philosopher in the field, despite her good intentions to try and model this phenomenon correctly, what she did was wrong. There is no correlation between the sound and the disk shattering. Both are caused by a gunshot that she did not know of. There we can see the shooter. And it is the shooter who is in fact destroying the disk, which is launched on the side by a disk launcher. When faced with endogeneity problems of this kind, the problem is that the relation we observe could be positive, could be negative, could be non-significant. In fact, we don't know what the true relationship is when we omit important causes. What causes endogeneity? There are three major reasons. The first one we just saw was omitted variables. And these come in many different kinds of forms. I just showed you one example where we omitted a common cause. But there are many different kinds of omitted variable biases. For example, omitting fixed effects. Many researchers, especially those who use what's called HLM models or hierarchical linear models, estimate these models using random effects or random coefficients without checking whether the level 1 variables correlate with fixed or constant effects that are due to the higher level entity. A second interesting case of omitted variable bias is where we have omitted selection. In this case, there is a choice that has been had by the entity we are observing. For example, women who choose to work or who choose not to work. How can we estimate the relationship between education and how much a woman earns if we can only observe women who are working? We need to also observe the counterfactual. What would women who are not working, what would they have had in terms of their salary had they chosen to work? So we need to model this endogenous choice. This comes in many different forms. For example, leaders may choose to attend a leadership training program or not. Firms may choose to export or not. Certain companies may choose to use a certain strategy or not. This choice is endogenous. It cannot be used to predict anything. It's just like the gunshot noise. The third major cause is what is called simultaneity. By simultaneity, we mean that the model that we have, X predicting Y, could work one way. In other words, X is a cause of Y. However, Y is also a cause of X. So we have a backward causal loop going from Y to X. As you can see, X is caused by Y and an omitted cause that we don't observe, and Y is caused by X and also by an omitted cause that we don't observe. The problem we have when we estimate a relationship between X and Y, and simultaneity might be actually driving the results, is that the coefficient that we estimate is actually wrong because it consists of two coefficients. So we might observe a coefficient of 0.50, but that doesn't mean anything. One could be going positive direction, another could be going a negative direction. For example, leaders change their leadership style as a function of follower performance. If a follower has bad performance, the leader might use a negative leadership style, one that gives negative feedback. If the follower has good performance, the leader might adjust their style as a function of that good performance. Thus, what we observe is actually not trustworthy. It is consisting of two components. Very often researchers say, well, the observed correlation that we have might be because X is causing Y or because Y is causing X. No, that is wrong. These researchers don't get it. The correlation we observe is not true. It's not correct because one correlation could be positive, the other could be negative. And these could be of different signs, of different magnitudes. In fact, what the researchers are doing is correlating the sound of the gunshot with an outcome. There are many other causes of endogeneity, including measurement error, which is a special case where X is actually exogenous but is not precisely or reliably measured. There's also what is called common method variance. Many researchers don't realize how bad common method variance can be. But in fact, if there is a problem of common method variance, we just don't know what the true relation can be. For example, suppose I ask you to rate your boss on a certain leadership style, and then I ask you if you like your boss. Or I might ask the questions in the other sense. Do you like your boss? Say you say yes. Are you very impressed with the leadership style of your boss? Is your boss a good leader? Well, you're more likely to say yes, given the first response. Now, it was very blatant the way I asked the question by saying, do you like your boss? Questions may be asked in more indirect ways, but they may be driven by a lurking variable, Z, which is driving the relationship between X and Y. And we just don't know what the true relationship will be if we have an omitted cause, if we have endogeneity. How do we get rid of endogeneity? Very simple. The fail-safe way to do it is with an experiment. In an experiment, X is exogenously manipulated. In other words, it varies randomly. Because it varies randomly, it will not correlate with anything in the dependent variable that we haven't measured. Let me give you an example. Suppose we want to try the efficacy of a treatment, whatever that may be, leadership training, a medicine, what have you. So we have a sample of individuals, let's say 100, and what we will do is we will use some kind of random mechanism to assign these people to a treatment group and a control group. We might have alternative treatments that doesn't matter. Suppose we have a treatment group and a control group. Because we randomly are assigning the people to either the treatment group or the control group, the groups at the beginning are exactly the same on any observed or unobserved variable. And that is very critical, because if the groups are exactly the same on every observed or unobserved variable, if there is a difference in them after we administer the treatment, that difference can be due to only one thing, that is the treatment, because there is nothing else that might possibly explain why we observe a difference in the groups. The groups were exactly the same in the beginning. So, the strength of the experimental design is that we can observe what is called the counterfactual. What would the treated group have received had it not received the treatment? That's what we observe in the untreated group. We can make a valid causal claim with an experiment. Remember, with an experiment we can be sure that no omitted causes correlate with the treatment. The groups are the same in the beginning. We can observe the counterfactual at the group level. Causal claims are valid. Experimental methods are one way to deal with endogeneity. There are other ways, a bit more complex, that borrow a lot from econometrics. I would like to depict the relationship between X and Y using Ballantyne's. This example is taken from Kennedy's Introduction to Econometrics book. Imagine here we have the two variables, Y and X. And the overlap that they have, where it intersects, is actually the percentage of, say, overlap or variance that is shared between the two variables. And that is actually what we want to estimate when we estimate an ANOVA model or a regression model. Assume that is the slope, beta. Of course, Y depends on X, but Y depends on other variables that we have not measured. I'm just going to add one in here, M. Now, because we have exogenously manipulated X, X does not overlap with M at all. It is independent of it, or it is orthogonal to it. Therefore, what we estimate in terms of X predicting in Y, the slope coefficient, is actually consistent. By consistent we mean that it reflects the true value as the sample size will increase. But even with experiments we can have endogeneity problems. Unbeknown to some experimentalists, I've noticed this very often in psychology, sometimes we actually might measure two dependent variables in an experiment, Y1 and Y2, and we want to estimate the causal effect of Y1 on Y2 as a function of X. So for example, subjects were randomly assigned to treatment, we call this X, and they were then measured on Y1 and Y2. Now, suppose that Y1 and Y2 share a common cause, which is possible because they were measured at relatively the same time. Suppose they were exposed, the participants, to a certain leader, and perhaps they liked the leader or not because of what the leader looked like. That's got nothing to do with the treatment that was administered. Therefore, if one tries to estimate the causal effect of Y1 on Y2, there is an endogeneity problem again between Y1 and Y2. And this endogeneity problem needs to be acknowledged. By acknowledged, we mean that the causal structure of the data must be modeled correctly. That is, X causes Y1 and Y2, but there is a common cause linking Y1 to Y2 that must be modeled. This correlation between the two disturbances must actually be modeled in the estimation procedure. Very often they do not do that, and if it is not done, the correlation then that is estimated between Y1 and Y2 will actually be misestimated. It will be wrong. The solution to this problem is very simple. It is to use the two-stage least squares estimator, 2SLS. In this case, X is known as the exogenous variable or the instrument which is used to help identify the causal effect of Y1 or Y2. How are we going to do this? We will find the portion of variability that X and Y1 share that overlaps with Y2. However, we must model this causal structure correctly by correlating the cross-equation disturbances. Going back to our Ballantines, so you can understand the nature of the problem, suppose we wish to estimate the relationship between y1 and y2, the causal relationship that is. Unfortunately, y1 and y2 share a common cause, which is q. As you can see, the portion where q overlaps with y1 and y2 is what is going to cause the endogeneity problem. This must be correctly acknowledged in the estimator. Now, if we just estimate this relationship between y1 and y2, as you will see, the overlapping area consists of a true component, but it also consists of an error component, and that is where the three circles overlap. That portion of the variance in the yellow circle is going to be incorrectly estimated if we use what's called the normal OLS, or ordinary least squares estimator, or maybe even maximum likelihood. It doesn't matter which estimator we use, but if we don't acknowledge the correct causal structure and find an instrument that is exogenous to the system of variables, we cannot identify the causal effect of y1 on y2. The instrument in this case is x. As you can see, x overlaps both with y1 and y2. Because x is exogenous, it does not overlap at all with the omitted common cause q, or any other causes, and I have not put them all in the model. We are just isolating q just to demonstrate the point. So what the estimator is going to do is it's going to look at the share of overlapping variance that x has with y1 and y2 to estimate the relationship of y1 with y2. Even though it's only using a smaller portion of the overlap of y1 with y2, it will still estimate it consistently. In other words, what coefficient we will find will be correctly estimated even though we use less information. This portion of the variance is what I call in the picture y1 hat. y1 hat is the predicted value of y1 that is due to x. Now, this predicted value has a very special property. It does not overlap with q at all, as you can see in the diagram. This is the actual two-stage least squares estimate, which can be estimated using two-stage least squares or maximum likelihood. I will show you in a minute how. What's important to do is to correlate the two disturbances, the disturbances of y1 and y2. That is, you have to acknowledge in this estimator that y1 and y2 are endogenous and that they potentially share a common cause. The correlation between these two disturbances, as I indicate in the Ballantines, is actually what the Houseman test estimates. So let me show you how to estimate this correctly. But first we will start off how to estimate it incorrectly. Now, usually what is done in these cases is that y1 is used as a predictor of y2. The problem is that y1 actually correlates with the disturbance in y2. In other words, this correlation is not zero. Beta 1, the relationship between y1 and y2, will in fact be inconsistent in its estimation. It won't be correct. Now, the correct way to estimate this model is to actually use the instruments to predict y1 first, and then to use the predicted value of y1 to predict y2. To do that, we must correlate the disturbances of the two equations. In other words, the disturbances of y1 and y2. So this disturbance correlation I call psi1. Now, if this correlation psi1 is not zero and it is estimated, we will kill endogeneity. If psi1 is not zero and we don't estimate it, we're going to have a big problem. And this big problem is just like we did before. If I can go back to the previous figure, it's as if we never used the instruments to predict y1 and use the predicted value of y1 to predict y2. In other words, constraining that covariance between the two disturbances to zero is going to give exactly the same and inconsistent wrong estimate as if we never had z or q in the model. And this is how many researchers go about testing such causal models. They have two endogenous variables, They may have exogenous variables from an experiment, ideally, but they don't use them in the correct way to estimate the relationship between y1 and y2. If the two variables that are endogenous share a common cause, this must be acknowledged in the estimator. Let me demonstrate to you a specific case with simulated data. This data is available on my website, and I encourage you to download it and play around with it in different programs to see whether you can obtain the same estimates that I do. So, suppose the model that generated the data, in fact the true model underlying the relationships between the two variables, is depicted as such. We have x that causes y, but we have q that causes both x and y. We also have two instruments, m and n, that are exogenous. They don't correlate with u, with e, and indeed with q. So what we're trying to estimate is the causal effect of x on y. And this causal effect is supposed to be minus 0.30. So we can estimate this model correctly, even if we don't include q in the model, as long as we correlate the two cross-equation disturbances. As you can see from the simulated data, and here the data are quite large, I have a sample size of 10,000 observations, we see that this two-stage least squares estimator recovers the true parameter almost precisely. It estimates it to be minus 0.29. Remember, the true estimate was minus 30. Now, if this is estimated the usual way, the OLS way, where this correlation is not acknowledged, it's as if we were doing two separate OLS equations. So even though you estimate the system of equations simultaneously, and if you do not correlate the cross-equation disturbances, it's as if you had estimated two separate equations that links them with nothing at all. In this case, when we regress y on x, we obtain an estimate of 0.03. Remember, the true estimate was minus 0.30. So we are way off in what we have estimated. Try this yourselves. Simply take y and regress it on x. You will get an estimate of 0.03. That's the observed correlation. This is completely wrong. So you may use all the fancy big hammers and structural equation modeling programs. But if the model, firstly, does not have exogenous variables to identify the effect of x on y, you cannot get the correct estimates. Second problem is, if you don't acknowledge the endogeneity between the two endogenous variables, you're not going to get correct estimates. Now, here's the million Swiss franc question. And for viewers in the United States, be assured this is a lot of money. It's actually 1.2 million bucks. Where do we get instruments from? In experimental design, it's very easy to get an instrument. That's the variable that was exogenously manipulated, or variables. And ideally, you'll have more variables than you have endogenous regressors, so that you can estimate what's called an over-identification statistic, whether the structure that you have in the data, the causal structure, is actually valid. So what that does, in fact, it compares the model that you have with what it observes in the data, just like as if you are comparing an architectural plan of a house versus what was actually built to see how close it was. So the closer the model is to the data, the more likely the model generated the data. So it is good to have instruments, to have at least a couple more than what we have in terms of endogenous regressors. Where do we get instruments if we haven't done an experiment? There are many creative ways that you can go about getting instruments. Economists have identified many interesting ways to do it when you want to, for example, estimate the effect of firms on performance, or country level variables on country level performance or on firms. There can be geographic instruments, there can be distance instruments, there can be vectors of malaria, many different ways. In psychology, for example, one can use the IQ of a leader, or any kind of fixed or constant effect that is genetically determined. So we talk about this in the paper published in the Leadership Quarterly, and the title is On Making Causal Claims. So if you're interested to find out more about it, please refer to the paper. To summarize, if x is not exogenous, its relation to y is suspect. and it has to be corrected using some kind of corrective technique which will kill endogeneity. There are many, many cases of this in the literature, and the paper to which I referred to, published in the Leadership Quarterly, we found that even in very, very good journals, in top journals in management and applied psychology, that estimates were severely compromised by using incorrect modeling procedures. So recall, we cannot regress Y, satisfaction of followers or what have you, on LMX, leader-member exchange. LMX is endogenous. We cannot use a hierarchical linear modeling estimator which looks at random effects when level 1 variables could correlate with the fixed effects. The fixed effects are an omitted cause. We cannot regress company performance on an endogenous choice, for example, using a certain control strategy or not using it, because the choice is endogenous. It has to be modeled correctly. And that's exactly where James Heckman, in fact, won the Nobel Prize in 2000. The procedure that's named for him, the Heckman two-step, he found out a way in which he could correct for this endogeneity and reproduce a true counterfactual, just like in an experimental design. Thank you for taking the time to listen to this University of Lausanne podcast. If you're interested to find out more information about endogeneity and how to correct for it, please refer to the following paper. The paper is available on my website, or if you wish, you may email me and I'll be very glad to give it to you. Before closing, make sure to think about the supposed causal effect that someone is trying to convince you of. Was the claim made in the context of an experimental design? If not, is it possible that there are omitted causes that haven't been correctly modeled? Were instruments used to assure that the causal direction of the effect of an endogenous regression can be identified on a dependent variable? If there's any cause for doubt, don't trust the results of the study that has published them. Remember, endogeneity is like a disease. It must be stomped out in every one of its forms. It's not ethical, neither economical, to base policies or practices on procedures that might not work. Thank you for listening to this podcast.